Welcome to another video on differential equations and their relation to modeling. This time we take a look at systems of ordinary differential equations with a potentially very large number of unknowns. And the specific example we take a look at are the differential equations that appear in Newtonian celestial dynamics. These are nonlinear second-order differential equations that describe the movement of celestial bodies subject to gravitation. Now, celestial dynamics is a very ancient topic. I mean, even in ancient times, long before history, people were interested in understanding the movement of the firmament. They were looking at the stars at night and were wondering, okay, why do the stars move? They were taking a look at the moon, they were taking a look at the sun, and they tried to make sense of their movements. And then over the millennia, people developed mathematical models that describe celestial dynamics. Celestial dynamics is a study of the movement of planetary bodies or celestial bodies. And celestial bodies in this context can be stars, it can be planets, it can be asteroids, it can be on a larger scale entire galaxies. In celestial dynamics, all the celestial bodies are modeled as point masses. So we disregard the fact that most of these bodies have some volume, just model them as points. Each of these points has a mass. And to every point, we associate their position and their velocity in three-dimensional space. Now, if it weren't for the presence of gravitation or other forces, every planetary body would just move from their position in the direction of their velocity, and not much would happen. But, well, in the universe that we know, we have forces acting such as gravitation. And on a celestial scale, gravitation is a dominant force. Now, there are different models, of course, to describe the influence of gravitation on celestial dynamics. And the current model is the theory of relativity developed by Albert Einstein. But in this video, we take a look only at a simplified model, namely the Newtonian dynamics and the Newtonian theory of gravity. Let us briefly review the ideas of Newtonian dynamics. So we have our celestial bodies. For example, here in this picture, we've got a star, we've got a planet, we've got an asteroid. They're at certain positions, and the red arrows are supposed to be velocity vectors, which describes the direction and magnitude of their velocities. But then between these massive bodies, there are gravitational forces acting. Between each pair of these bodies, we've got forces that pull these bodies together, and that means that these act as acceleration of these bodies. Now, the strength of these forces, or the strength of the acceleration and their direction, of course, then depends on the position of the bodies. And that leads to a system of ordinary differential equations which describes the Newtonian theory of celestial dynamics. The most simple setting of Newtonian dynamics is the dynamics of two bodies that move throughout space and interact via gravity. So suppose that we have two massive points, literally massive in the sense that each of them has a mass, and their respective masses are m1 and m2. We are interested in the movement of these bodies over time, so we would like to keep track of their position. if we fix a coordinate system in three-dimensional space, then we can describe each position by a three-dimensional vector, which includes the x, y, and z coordinate. And so for any time t, we let p1 of t be a three-dimensional vector, which describes the position of the first body, and we let p2 of t be a three-dimensional vector, which describes the position of the second body. Now, in the context of celestial dynamics, we're also interested in the velocity vectors. In Newtonian dynamics, the velocity of every particle is also a three-dimensional vector, which describes the magnitude and direction of its velocity. We would like to keep track of those over time too. So we let v1 of t be a three-dimensional vector, and we let v2 of t be a three-dimensional vector. And these are the respective velocities of the first and the second particle. As you remember from physics, the velocity is a derivative of the position. And that is also true for the velocity vectors. So let us just state that v1 of t is a derivative of p1 of t, and v2 of t is a derivative of p2 of t. Due to gravity, there are forces acting on these 2 points. And of course, the forces also vary over time, depending on how the particles move. So for any time t, we let f12 of t be the force that is acting on the first point, pulling it in the direction of the second point. And conversely, we let f21 of t be the force of the second point, be the force acting on the second point that pulls in the direction of the first point. Both f12 of t and f21 of t are again three-dimensional vectors. So let g be the gravitational constant. The formula for f1 of t is g times m1 times m2 divided by the Euclidean norm of p2 of t minus p1 of t to the square, multiplied with p2 of t minus p1 of t divided by the Euclidean norm of p2 of t minus p1 of t. Conversely, the force vector f21 of t is g times m2 times m1 divided by the Euclidean norm of p1 of t minus p2 of t to the square, and multiplied by the vector p1 of t minus p2 of t divided by the Euclidean norm of p1 of t minus p2 of t. Now, if you take a look at these formulas, you see that they're given as the product of a scalar times a vector. So let us, for example, take a look at f12 of t. So the first term here, g times m1 times m2 divided by the square of the distance between the 2 points, is a scalar, of course, and that tells us the magnitude of the force. And the second term here, that is the unit vector in the direction pointing from the first particle to the second particle. And conversely, f1 of t is given by a scalar which denotes the magnitude, and that scalar is multiplied by the unit vector pointing from particle 1 to particle 2. What we can see is that the force will decay quadratically as the particles are moved further and further apart. But conversely, as the particles get very close, the force will become stronger and stronger. In fact, the closer they are, the force will eventually go to infinity. In order to derive a system of ordinary differential equations, we recall the following fact from physics, namely the accelerations of the two bodies are the second derivatives of their positions. So p1 prime prime of t is the acceleration of the first particle, and p2 prime prime of t is the acceleration of the second particle. And these accelerations are related to the forces by the following fact of Newtonian physics, namely force is the same as mass times acceleration, which leads us to F1 of t is equal m1 times p1 prime prime of t, and F21 of t is equal m2 times p2 prime prime of t. Okay, with these two last equations here, we can finally assemble the second order formulation of Newtonian dynamics for the two-body problem. The system of differential equations that we get here is the following. We've got m1 times p1 prime prime of t is equal the definition of the force vector f12 of t, and m2 p2 prime prime of t is this equal the second, that is equal the definition of the second force vector. Now let's also simplify this a little bit. We divide both sides by the mass. So we have the following compact form of the system of ordinary differential equations of second order. p1 prime prime of t is equal g times m2 times the Euclidean norm of p2 of t minus p1 of t to minus 3 multiplied by p2 of t minus p1 of t, and conversely p2 prime prime of t, the second derivative of p2, is the same as g times m1 times the Euclidean norm of p1 of t minus p2 of t to the power minus 3 multiplied by the vector p1 of t minus p2 of t. So we've got two differential equations of second order, and I would like to point out here that the two unknown functions here, p1 and p2, are themselves vectors. So actually each of them is constituted of three coordinate functions. So to each of these equations here, to each of those two equations correspond actually three equations. So if you write this down in terms of coordinates, then actually we have 6 differential equations that are coupled with each other. I hope it is clear that using this vector notation actually simplifies the exposition of Newtonian dynamics. Let me interject this screen here. So in the two-body problem, we have this formulation in terms of two vector-valued unknown functions, p1 and p2. And if you struggle to make sense of that, I suggest you take a look at the screen here. And what I've simply done here is I've rewritten these two differential equations with the two vector-valued unknowns in terms of 6 differential equations with 6 scalar-valued unknowns. I've only unwrapped the vectors. So for the two position functions, I've simply written down the 3 respective coordinate functions. So we have the x, y, and z coordinate of the first position and the x, y, z coordinate of the second position. it should be clear from the screen that writing this down in terms of scalar valued functions is quite cumbersome. So we actually do save some cognitive effort by using this vector valued notation.
Okay, again, we have second-order differential equations, but for applications in numerical analysis, we would like to rewrite these in first-order formulation. So let's do that. Similar to the situation for the harmonic oscillator, we use auxiliary variables for the velocity in order to reduce the system to first-order formulation. The velocities were already introduced above. So let's just recap. We've got v1 of t equal p1 prime of t, and v2 of t is equal p2 prime of t. And if we take these two equations and take the derivative on each side, then we also see that the derivative of v1 of t is the same as the second derivative of p1 of t, the acceleration of the first particle, and v2 prime of t is equal p2 prime prime of t, the acceleration of the second particle. So putting that all together, we get the following first-order formulation for the two-body problem. Namely, v1 prime of t is equal g times m2 times the inverse cubic power of p1 of p2 of t minus p1 of t multiplied by the vector p2 of t minus p1 of t, and conversely, v2 prime of t is equal g times m1 times the inverse cubic power of p1 of t minus p2 of t multiplied by the vector p1 of t minus p2 of t. And then we also need to explicitly state that the velocity variable and the position variable are coupled. So we add the following two equations, namely p1 prime of t is equal v1 of t, and p2 prime of t is equal v2 of t. We have wrapped this in a rug so far, but we also need initial conditions. So it is intuitive that at each point in time, the state of the system in Newtonian dynamics for the two-body problem is defined by the two positions of the particles and their two velocities. So for that reason, I give initial conditions at t equals 0 for the positions of the two particles and their velocities. So let us explicitly state that p1 at t equals 0 is equal p1 0, p2 of 0 is equal p2, v1 of 0 is equal v1 0, and v2 0 is equal v2 0. And again, all these four variables here are vector valued. So these four equations here actually are compact notation for 12 equations with 12 unknown scalar valued functions. The two-body problem concerns the movement of two bodies in space subject to Newtonian gravity. And if we can do such a theory for two bodies, then it's also no big surprise that we can do the same thing also for n different bodies. And that leads to what is known as the n-body problem. So again, suppose we have massive points, and this time we suppose that massive points with m1, m2 up to mn. So again, we keep track of the positions of these 2 points over time. For any time t, we denote their respective positions by the following vector-valued functions, namely p1 of t, 2 of t, up to pn of t. And then again, each particle also velocity, which is time t is a 3-dimensional vector, and the respective velocities are denoted by v1 of t, v2 of t, up to vn of t. And let's also recall that the velocity of a particle at any time t is the derivative of the position of the ith particle at every time t. So we have got these n different particles, and of course all these particles are interacting with each other via gravity. Now, we recall with the two-body problem, we are considering the interaction of 2 particles. So basically we had only 1 interaction, but this time we have got n particle and gravitational interaction between each of the particles. So for each pairs of particles, we need to consider force vectors. And formally, well, we let Fij of t be the force that is exerted on the ith particle due to gravitational attraction to the jth particle. And the law of gravity tells us that the force Fij of t is given as follows, namely g times mi times a multiplied by the Euclidean distance between the ith and the jth particle to the inverse second power multiplied by the unit vector pointing from the ith particle to the jth particle. Formally, Fij of t is equal g times mi times mj multiplied by the Euclidean norm of pj of t minus pi of t to minus 2 multiplied by pj of t minus pi of t divided by the norm of pj of t minus pi of t. So for every point, we have got force vectors for every other point, and each of these forces acts on the ith particle. So if you take a look at the ith particle, then there's a force vector acting on the ith particle for every of the other particles. And the total force that is exerted on the ith particle is given as follows. Namely, it's just the sum of all the force vectors. So formally, the total force exerted on the ith particle at any time t is Fi of t, that's the notation that we choose, and Fi of t is the sum of all the Fij, where j is different from I and between 1 and n. Now working towards an ordinary differential equation, or rather a system of ordinary differential equations, we use again an important fact of Newtonian dynamics, an important of classical physics, namely the total force that is exerted on the ith particle is related to the acceleration that this particle experiences by the formula mi times I prime of t is equal Fi of t. In other words, the total force exerted on the particle I is the mass of the times its acceleration. Okay, now we again have all the ingredients to set up a system of ordinary differential equations of second order. So just plugging in definitions, what we get is mi times pi prime prime of t equal g times mi times summing up j from 1 to n, where j is not equal I, and each of the summands is mj multiplied by the Euclidean norm of pj of t minus pi of t to the inverse cubic power multiplied by pj of t minus pi of t. And okay, if we do again a bit of simplification, what we get is, as we divide each of these sides by the mass of the ice particle, pi prime prime of t is equal to g times summing up j from 1 to n, where j is not equal I, mj times the Euclidean norm of pj of t minus pi of t to minus 3, multiplied by the vector pj of t minus pi of t. Let us recall at this point that the function pi actually is constituted by 3 functions at once, the coordinate functions for the x, y, and z coordinate. So if we unwrap all this, then actually this is a system of 3 times n unknown functions that take scalar values,
Where did this bring us? A system of n second-order differential equations in n vector-valued unknown functions. Now, just as before, you would like to rewrite that system of second-order differential equations in terms of first-order differential equations. And for that purpose, we introduce again auxiliary variables for the velocities of the particles. And then again, we also need to specify initial conditions. For this enlarged system, we need initial conditions for the position variables and the velocity variables. So this works very similar to what we've seen before. And let us only summarize how the final system of first order is going to look like. So the first order formulation for the n-body problem consists of the following. Namely, for every particle with index 1 to n, let us say we pick the ith particle, then we get the differential equation vi prime of t is equal g times summing up j equal 1 up to n, where j is not equal I. And what we sum up is mj multiplied by the Euclidean norm of pj of t minus pi of t to the inverse cubic power multiplied by the vector pj of t minus pi of t. And then we also need to explicitly couple the velocity variable and the position variable of the ith particle. And that is done via the differential equation pi prime of t equal vi of t. And since we have a position variable and a velocity variable for each particle, we also need to specify initial conditions for each of those two for every particle. So we just say that pi at t equals 0 is equal pi naught, and vi at t equals 0 is vi naught, where pi naught and vi naught are the initial positions and initial velocities. And since we work with n different particles, In total, we're going to have 2n differential equations for 2n unknown functions, vector valued functions, 2n initial conditions. And if you really want to unwrap this all in terms of scalar valued functions, then of course we see that we can also rewrite this entire thing as 6 times n differential equations and n unknown scalar valued functions. And then we also need to specify 6 times n scalar valued initial conditions. Because for each particle, we have the x, y, and z coordinate of the position over time and the x, y, and z coordinate of the velocity over time. Such particle systems are quite an important topic in computational science. So much resources in research and also in computational equipment are dedicated to the simulation of cosmological dynamics, even on maybe a galaxy scale. So sometimes these particles are just stars, or sometimes each particle in simulations represents entire galaxies. As you can imagine, since every particle has gravitational interaction with every other particle, it can be quite complicated or quite resource intensive to conduct numerical simulations for such large systems.